Hello. In this video, I want to look at some examples that are similar to questions you might see on the Calculus AP exam, Form AB. The first one involves limits. The two following that are the the power rule and the quotient rule for derivatives. The fourth example is the L'Hopital's rule, where we need to assess limits using derivatives, and finally implicit differentiation. The nice thing on standardized tests, if you ask me, especially when it comes to math, is that we have possible answers already set out for us. And in my opinion, for math exams or for objective sciences, compared to English, for example, we have fewer distractor options in the solution sets here that we can choose from. And so if we just follow the basic structure and the pattern and the technique as we're supposed to and minimize our simple math errors, then it's very likely that we'll come up with the correct answer. So now some of you might know automatically that if we're taking the limit as x approaches 0 of this rational expression, where we have polynomials on the top and bottom, and both the top and bottom, numerator and denominator, are expressed in the form of binomials, where the highest power of x is 2, and that is shared on the top and bottom, then the limit as x approaches infinity is just the ratio of leading coefficients there, because both the numerator and the denominator have the same power of the variable. But in order to get to that, a long time ago, before people knew the shortcut, they'd have to use some algebraic simplification and somehow manipulate the expression using algebra to come up with that answer. So let's have a quick look at how we might do this in long form. Well, to multiply the entire rational expression by x squared over x squared is just multiplying it by 1. Anything multiplied by 1 doesn't actually change the value. So let's multiply this entire rational expression by x squared over x squared, and then we can change the numerator and the denominator to whatever that polynomial was, that quadratic polynomial was, and divide it each term by x squared. So 5x squared over x squared is 5, and then we're just going to simplify, get rid of the x on top, rid of the exponent on the bottom. This term will stay the same. We're going to get rid of both x squareds in the first term here. We're going to get rid of that exponent on the bottom and the variable on top here, and keep that the same. And we end up simplifying this to get 5 minus this over 4 plus this. Well, as we assess any limit as x approaches 0 for a rational expression where the denominator is phrased in terms of that variable, then any k or constant over x to the n, where n does not equal 0, so including x to the first power. As x approaches 0, well, this value approaches 0. Meaning that if we divide anything by a very large number, a very, very large number, then it comes close to 0. So when we can imagine the diminishing function as x increases in value. If x is 10, then x to the first is 3 over 10, or 30%, and x squared is 3 over 100, or 3%. X cubed is 1,000, so 3 over 1,000 is 0.3%. And so we would see that number grow smaller and smaller and smaller, close to 0. So 5 minus 0 plus 0, or what's approaching 0, is still 5. Same with the bottom. 2 divided by any large number, any extremely large number. 5 divided by any extremely large number. Even though the exponent is different, it's still a very, very large number. Still infinity or infinity squared. There are different infinities, but in this case, those don't matter. And so 2 and 5 divided by extremely large numbers just turn to 0, and we get the ratio of those leading coefficients, 5 over 4. Next, let's have a look at the basic power rule. This is the first type of derivative that you'll learn in your pre-calc or calc classes. So we have f of x equals 5x to the 4/3. This exponent is a fraction, but that doesn't change our power rule. We're just going to take that exponent, drop it down in front of the coefficient, reduce the exponent by 1, and so 4/3 minus 1 is the same as 4/3 minus 3/3. 4 minus 3 is 1, and then we keep the denominator the same when doing fractional subtraction, we subtract only the numerators, we have a common denominator, 4 minus 3 is 1, and so we have 1/3 here. So there is our general form for the derivative. Now all we have to do to assess that at f prime of 8 is substitute 8 for x. So we get 4/3 times 5 times 8 to the 1/3, or the cube root of 8. If we recall, the cube root of 8 is 2. 2 times 2 is 4, times 2 is 8, so the cube root of 8 is 2. This is pretty easy. We didn't have to use a calculator. And all we have to do then is multiply. 4 times 5 times 2, or 4 times 10 is 40, divided by 3. B. Pretty simple. Next one. Looks like we have a quotient here. We're going to have to apply the quotient rule when trying to assess f prime of x. We could go directly to the quotient rule right now, but it would take a little bit longer. So if we look at the terms in the numerator and denominator, if we wanted to speed up the process, we can take something out of both the numerator and the denominator, and that is the same thing for the numerator and denominator. So while we could go directly to the quotient rule now, it might save us some time on a standardized test and make it less likely that we make an error. If we take out x from both the numerator and denominator, then we could redistribute that if we wanted to come back to that original rational expression. X times 3x is 3x squared, x times 1 is x times 3x again, 3x squared, x times -1, negative x. But we can cancel these out, or x divided by x equals 1, so we can remove those from the situation here. And we get a new rational expression to which we can apply the quotient rule, which says if we have a rational expression where both the top and bottom are polynomials or are functions, then we can take the derivative of that u, which is the numerator, over v, which is the denominator, by expressing it in terms of v, which is the denominator, times the derivative of the numerator, minus the numerator times the derivative of the denominator, over the denominator squared. And so if we just carry out the math here, then f prime of x is the denominator, 3x minus 1, times the derivative of the numerator, the derivative of 3 times a variable to the first power, or any such coefficient variable to the first power, is just that coefficient, minus u, or the numerator here, times the derivative of the denominator, which is the same because these constants just turn to 0. The x's disappear when we take the derivative, and we get 3 again, divided by 3x minus 1 squared, or the denominator squared. And let's leave this alone for now. I don't think we need to expand it. Generally speaking, we want to simplify. And if we can simplify the top such that one of these answers appears, then we don't have to do anything with the bottom. So if we want to expand, 3x times 3 is 9x, -1 times 3 is -3, -1 times 3x times 3 is -9x, -1 times 1 times 3 is -3, 9x minus 9x is 0, -3 minus 3 is -6, and it looks like C then is our answer. And so that was probably a little faster than if we wanted to work with the original rational expression and go directly to the quotient rule. So if and when possible, we should probably try to simplify before we use the product or chain or quotient rule. So this one here, we're taking the limit again. We've got sine x squared over x is our function. Now, if we think about the unit circle, then we know sine is the ratio from trigonometry. Sine is the ratio of opposite over hypotenuse. If you guys remember SOHCAHTOA, opposite over hypotenuse on the unit circle is the y component divided by 1, which is the hypotenuse on the unit circle. And so as x, or that y component on the unit circle, on our right triangle where the x and y axis will form, or the x and y component will form that right angle, and our central angle, theta, is the degrees from 0 moving counterclockwise in the unit circle. The ratio of that y component to 1 would be decreasing to 0. So we'd end up getting 0 over 1 when x approaches 0. The triangle would be incredibly slim, be very, very small. So basically be a straight line. We don't actually have much of a triangle as x approaches 0. And we know then that x, the length of that side, is in fact approaching 0 also. So we'd get 0 over 0, which is not an attractive limit to find. That's what's called indeterminate. 0 over 0 forms indeterminate. So when we look at any kind of test and we see an example question that asks us to find the limit, and it's a rational expression where on the top we have sine x squared or sine x or cosine x squared, some kind of trigonometric function, and then x on the bottom, it should throw up a light bulb, right? That we're using L'Hopital's rule. And so if we try to, if back in 11th or 10th grade or whenever you learned how to do limits before you learned any derivatives, if you tried to assess this limit, you might just end at that 0 over 0 form. This limit is a special variety that we need to apply this man's rule to. And that means we're going to take the first derivative of the numerator and denominator and then take the limit. And we might have to repeat that step again if we still get indeterminate form. And so the limit as x approaches 0 of our function here then is equal to, and there are proofs, this man spent a large number of days and hours and weeks and years proving this. And that's why it's called L'Hopital's rule, because he spent so much time on it. The limit of our function here is actually equal to the limit as x approaches 0 of, let's take our first derivative using the chain rule, if you remember. The first derivative, so the chain rule, we need to say, first let's look at what's inside function. The derivative of x squared is 2x, and then we're going to multiply that by the derivative of the outside function, derivative of cosine, sorry, the derivative of sine is cosine, and so we got 2x times cosine x squared. That's our derivative of the top. Derivative of the bottom is just turning into 1 because derivative of any variable to a single power is 1. And so anything divided by 1 is itself, meaning that the limit as x approaches 0 of 2x cosine x squared is just, let's take 0, 0 times 0. Well, 0 times 2 is 0. That means that this equals 0. 0 divided by 1 is still 0. Right? And so this 0 plugged into x here then removes any need even to assess cosine of 0 squared, although that would be easy enough to. 2 times anything, or 0 times anything, 2 times 0 times anything is 0. 0 times anything is 0. So if, again, it returned 0 over 0 for the top and bottom, we could take the derivative and do the whole process again. And depending on the complexity of the problem, you might have to do that 2, 3 times. That would be L'Hopital's rule. Next and last, looks like implicit differentiation. We're looking at dy dx. Now, derivatives are phrased in the form d dx, d over dx. And we have d over dx can only be calculated when we have all the y's on one side and all the x's on the other side. And we can't do that in this equation here. We've got our y's and our x's mixed up, right, in this middle term especially. And so what we need to do to find the derivative of this function is implicit differentiation. We got our x's and y's mixed up. We can't take d dx. And so first we're going to take the derivative of everything with respect to x. dx over dx equals 1, right? So we can take the derivative here. X squared is 2x, and that's dx dx, or times 1, minus 2 times, this is where it gets a little confusing. Since we have a y here, we're going to say dy dx. Right? We're going to keep x the same, we're going to say dy dx. And then we're going to add, because they're multiplied here, we're going to add to this term here, a y, which is the derivative of xy with respect to x. We get rid of that x, we end up with y, and that's times dx dx over 1. This is just to keep track that we've actually taken the derivative. So the derivative with respect to x of this term is negative 2 times the sum, since these are multiplied, of x dy dx, because the derivative of y with respect to x is dy dx. And we're going to add to that y times dx dx, because the derivative of x with respect to x is 1. And then we get plus, we're going to take that exponent, move it down here, and we get 2 times 3 equals 6. So this situation is special because we got x's and y's mixed up together. We're going to use that special phrasing there. So 6y, that's the basic derivative here of 3y squared, but then we need to say dy dx because we're taking it with respect to x, not with respect to y. And then anything and derivative of any constant is 0. Right? Next, we're going to simplify. Let's combine like terms. So we get 2x, and this is 1, so we get rid of that, minus 2 times x dy dx. We're just distributing the negative 2 to this term and to this term, minus 2 times y, and get rid of that because it's just 1, plus 6y dy dx. And then we're going to move our like terms to the same side. So we want to get those dy dx on one side here. So we're going to take negative 2y and 2x, move them to the other side. Negative 2y then becomes 2y, 2x becomes negative 2x. And so we get this equality here. Now we can factor out dy dx. So we've got dy dx as a common term between these two. We'll factor that out. We get dy dx times 6y. We'll just put the positive one first. Minus 2x, and that's equal to 2y minus 2x. And finally, we can divide out the term that's not dy dx to find that dy dx, which is our derivative, but it's a different type of derivative than we are used to usually working with. Right? So 2y minus 2x over 6y minus 2x. We can see 2 and 2, that's a common factor, 6 and 2, so all of these share a common factor of 2. We can divide out a 2 from the first two terms up top and from the first two terms on the bottom and eliminate those, and we end up getting y minus x over 3y minus x for implicit differentiation. And this middle part is really the tricky one. Right? So pay attention to that. Okay? And in future videos, I'll continue looking at more examples from the AP Calculus AP form. Thank you.